Hey everybody, welcome to week 4. Just a couple minutes, we'll get started. Hello Jarvis, hello Nils, hope you're doing well. Nice to see you. Hey Seaborch. Hey Dimitri. I'm doing pretty well, thank you. Hey Josh. Hey Orlando. Hey Drew. All right, 3 o'clock, let's get started. This week, a few things I want to talk about, kind of building on the concepts from previous weeks. We've been dealing with some UGen functions, so simple functions which, when played, produce sound. Just some basic stuff there. I want to dive into a few more details regarding UGen functions. Specifically, I want to talk about declaring arguments in the context of a sound function and how we can manipulate those arguments in order to control the sound with a little bit more flexibility than what we've been doing so far. So far, we've just kind of been playing a sound and stopping a sound, which is like, it only gets you so far. Also want to talk about envelopes primarily. So we'll spend a lot of time today talking about envelopes and how they're useful, mostly in the context of amplitude envelopes, so we can actually get a sound to fade in and fade out. So just overall giving ourselves the ability to exercise some more control over our sounds. All right, so I wanted to start today with a very simple UGen function. Let's see. We'll make a sine wave. And I suppose we could just play this, maybe sort of something. This would be sort of very simple. We're going to have to boot the server first. So we should be able to hear this. Lovely sine wave. Now, I want to do a couple extra things just so this is maybe a little bit more interesting. Emphasis on little. And introduce a couple of methods along the way. Now, normally, if we multiply the signal by some large value, this is kind of generally a bad idea because we're going to run into clipping. We're going to clip the meters. It's going to be pretty loud. But there's a method called soft clip, which is basically going to take a high amplitude signal and gently kind of force it back down into a normal range. So that will sound, if we just amplify it maybe a little bit, it'll sound kind of like this. And a little bit more. I'll turn this down a little bit. Well, I think I'm just going to turn my volume down. It should be reasonably loud for all of you. Is this sounding okay out there? I'm using a different interface today, so I'm just making sure the signal is still coming through on the stream loud and clear. Anyway, so we are amplifying the signal and then soft clipping. So we're basically doing a form of wave shaping here. It's just a little bit nicer. And let me also introduce another unit generator here. Seems good. Excellent. Thank you. If we don't exclamation point 2, then we just get mono sound in one ear. And we've been doing this exclamation point 2 as a way of just copying the signal. So it's an array of 2 signals, and that works pretty fine. But let's introduce another UGen here, which is on my list of essential UGens. That's in a video description last week or the week before that, which is pan2. Pan2 takes a monophonic signal, and you give it a pan position argument. We'll do 0 for now. And then it also has a level argument, which you can just think of like mul or just an amplitude scaling factor. So we'll put 0.2 here, just like we had previously. And so now we get signal in both channels. If we make this -1, it's on the left. +1, it's on the right. And, you know, something like 0.4 is going to be panned a little bit to the right, but not all the way to the right. So let's just set this at 0 for now. And there we go. We've got our basic sound function. And so we're going to kind of work with this throughout the lecture today. Now, the first thing I want to do is introduce the concept of separating function definition from function execution. Now, what we're doing here is we're doing both sort of in one go. We define a function. You know, we could say x equals or whatever. We want to give this a name. F equals this function dot play. So we're creating a function, and then boom, we're following that up with dot play. So we're merging these two processes. I want to separate these two processes out. So we're going to copy this, put it down here, and we're just going to take away the dot play. Run that. So it's exactly the same, except we're not playing it. We're just saying f is a function. It contains some stuff, and when we play this function, it'll make sound. So now we can say f.play, and we get our sound, right? So now we should probably give this resulting process a name. I'm going to call it x equals f.play. So now we'll be able to say x.free. So we're playing our function, storing the resulting synthesis process that sort of lives on the audio server in an identifier, a global identifier or global variable called x. And so we can then talk to x and say x.free. And this is kind of all we've done so far, right? So we've separated out the process into defining a function and playing a function. This is a critically important step because in the context of larger projects, larger compositions, it makes sense to divide your workflow so that there's a sort of setup phase where you define all of the things that make the sounds in your piece and kind of conceptually divide that and keep it separate from the execution, the actual playing process where you say, now you play, now you play, now you play, now you play together, now you stop, etc. And sort of doing it like all together, function.play. I mean, it works just fine, but it's very sort of quick and dirty. So this is a little bit more sophisticated. Okay, so now I want to talk about arguments. As you can see, the frequency of the sine wave is 220 hertz. So we hear meh, 220 hertz. Pretty boring. It would be great to be able to change this frequency. Now, it would be very tedious to have to go in here and be like, okay, 330, run this function, and here we go. Hooray, a new tone. Okay, next tone. And we go back here, and we're changing and running and changing and running. Obviously not the right way to do it, and this is where arguments come in. So I'm going to just once again copy this, bring it down here. All right, so we have a synthesis function. At the very top, we declare an argument. Sorry, no equal sign. Argument, space, freak, semicolon, and we put freak here. So we think of when we're in the context of a function containing unit generators that is meant to produce sound, we think of these arguments as like input jacks on a modular synthesizer, right? These are places where we can exercise dynamic control over the sound. So we can set this frequency to be a particular value, change it while it's playing, modulate it in other ways. So let's see how this works. Now, if we run this and then play it, doesn't work. Doesn't work because freq doesn't have a value. We declared it, but we didn't initialize it. So how does it know what the frequency is supposed to be? It doesn't. So it's a good idea to provide default arguments on the argument declaration line like this. So now, there we go. Just for a little variety, let's change that. And here we go. We're kind of doing the same thing again. We find ourselves tweaking values to say, I wonder what this would sound like. I wonder what that would sound like. And when you find yourself doing that, you should think to yourself, I should make an argument. So we'll call this like boost or something. Right. So now we've got freq 330, boost 4. All right, but we're still not doing dynamic control here. So once we play this function, because we've declared arguments, freq and boost, we can change those dynamically. And we do that by sending a set method, using the set method and sending a message to the synthesis process X. And this set message involves pairs of things. It can be one pair or multiple pairs, but each pair consists of a symbol representing the name of the argument, followed by a comma, followed by the value we want to give it. So let's give this a try. We've got this function. Boom. Right? So that is pretty exciting. Now, let's take a moment and revisit some concepts from last week. Now, maybe we don't want to have the same value every time, or maybe we don't want to manually specify values. Well, we can let SuperCollider do some of the work, right? Sort of like this. So we've run our function, and just run this line as many times as you want. All right, so while we're on the topic of set, I also want to show you another message in the same sort of category, release. Right? And we're done, so x.release. Now you might be thinking, hold on, what is the difference? Come on, Eli. Don't mess with me. So they are different, but if you just say x.release and x.free, you can't really tell the difference. But release, and we're sort of getting into the concept of envelopes here, release actually fades out a little secret envelope that is created for you when you play a function. When you do a function.play, there's a couple of things that happen in the background. SuperCollider kind of tidies up for you and says, all right, you're being sloppy here. I'll give you an envelope. I'll give you a this and a that. So we can say release and then provide the number of seconds we want that release to happen. So we'll play it. So now we're getting somewhere. Right? Play it again. Right? All right, so we're making some progress here. Let's see. Now, okay, another thing to notice is every time we do f.play, we are playing this sound function with these arguments at their initial values. Frequency 330, boost 4, right? Now what if we want to start this function at a different frequency instead of 330, right? Well, we can do that. And to do this, we take a look, we open up some parentheses on play. Just like the release method can optionally take a time in seconds, so can the play message. And this is a little bit different. It's not going to be a simple number. But the way play is defined for functions is it gives us a bunch of arguments. Now, a lot of these are going to be nonsense at this point. Target, outbus, add action. Some of these are, So right now we're just going to focus on this last argument, which is kind of ironically called args. And you can skip over to args by declaring it directly, putting a colon. And then you're going to provide an array. And this array is going to be quite similar. It's going to contain basically the same thing you have here, where we're going to say freq, comma, and then whatever you want your initial frequency to be, say 440. So not only can we change declared arguments while the sound is playing, but we can also initialize the sound with desired value. So this is the crux of why argument declarations are so valuable, because all of a sudden you don't have this static entity where it's always the same frequency, always the same amplitude, always the same blah, 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 blah. So really quite useful. And going back to setting for a second, there's a lot of possibilities that go far beyond a manual static value that we provide, or just doing complete randomness. And think back to the topic about arrays, like last week. So we can say, let's do a little, let's prepare it ahead of time so we don't have this tone sort of in our ears. So we're going to set the frequency to, let's do the array. Remember, there's a shortcut here. You know what? First, I'm gonna show. Okay, so many things I want to talk about here. The first thing is, it's not always convenient or intuitive to think in terms of hertz. We say, okay, I'm at 200 hertz and I want to go up by a major third, right? What are you gonna get out your scientific calculator and start doing powers of 2 to the, it's going to be confusing. So we can think in terms of MIDI notes, which is really handy. So for example, 60 is middle C. We just need to send a number, the message MIDI CPS, which converts from MIDI to cycles per second. So that's pretty easy, right? 72, that's an octave above. And so we get that value in hertz times 2. So very, very handy. For context, on a piano, the lowest note is MIDI note 21, and the highest note is 108. So, do with that what you will. So you can say 60.MIDI CPS, and let's just set this a few times. There's middle C. Right? So we got MIDI CPS. Now let's get back to arrays. And let's say we're going to do, let's say 35, 37, ... 79. Right? So this little bit of code right here is a syntax shortcut for creating the array 35, 37, 39, on and on we go. But we can't give this array to frequency, because frequency doesn't know what to do with an array. It's not going to work right. We need to choose one of these. Right? You get the idea. So this is an interesting way to deal with harmony. You can sort of pick an array of notes that belong to a particular collection, like a scale or a chord or some set, and then you can sort of select from those. So it gets sort of all right, and it can be sort of an interesting approach. Now we're gonna do next here. Let's see. Oh, okay. Now it's pretty. Let's actually say we want to make a bunch of these simultaneously instead of just playing one and then updating its frequency value. Well, we can do that. Let's do. Trying to think of an interesting musical thing to do. Let's say 40, 45, ... 70. So these are. Oh, you know what? I totally forgot something very important, which is this. I'm so sorry. This last example here, I was picking one of these values and just plugging it straight into the SINOSC. So it was treating these values as just values in hertz, 35 hertz, 37 hertz, etc. So this is what I meant to do. Yeah, that sounds much more like a whole tone scale. So my apologies there. And just by the way, for anyone asking questions, I'm trying to be a little bit more diligent about answering questions sort of after lecture's over, so at 3:50 or so, just to help me sort of keep on track. All right, so here, so now what we're going to do is I'm actually going to make multiple synths. I'm going to play this sort of one after the other. Let's give ourselves another, for now, let's just turn this down so it doesn't get too loud. And I'm just going to run this line a few times. All right, and now what we'd like to do is kind of start taking them away, right? All right. It ain't working. And maybe you can see why. Yeah, the fourths are nice. I like the fourths too. We run this line once. X equals, sort of the language side variable x is set equal to this resulting synthesis process, which is the result of f.play. It's a tone at a particular frequency. And then we run it again. And then we're saying to the language, okay, x now equals this new synthesis process. And x now equals this third synthesis process. And x is like, okay, now I'm this thing. Now I'm that thing. Now I'm this third thing. And by the end of it all, x is pointing to the most recent one that we created. So we can release that last one. But then if we say x.release again, it says, oh, hold on, that one's gone. Like I don't know what to do. I can't. So this is the wrong way to do it. And one significantly better way to do it is to use a concept from last week, which is arrays, right? So let's copy this line and bring it down here. So let's say A equals the empty array. Boom. We have an array. It's empty. And now we're going to say A equals A.add this thing. Right? So this is what we are adding to A. Basically, it's this thing I keep saying synthesis process, and the actual name for it is a synth. We'll get into what synths are probably next week, but for now, just think of it as a little synthesis organism that lives on the server that's making sound, right? So now let's add a few more of these, right? So we've got our empty array A. We're going to add a synth. We're going to add another synth and another. Okay. So now, A.size, we've made 12, right? And I'm going to turn this down just so we can hear ourselves think for a second. Now, we can go through and say, okay, A, add 0, release yourself, right? Do that. And then, A, add 1, A, add 2, right? But doing this repetitive task should make you think, hold on, iteration. This is where do and collect. Exactly, A.do. So let's do that. So A is an array, and it contains 12 synths, because we just checked its size here. I should keep that line, A.size, right? So we got 12. Doesn't really matter how big it is. It could be any size we want. We're going to iterate over the array with A.do and pass in an argument which is going to represent each synth in order, and we say n.release. And let's just do a 3-second fade out. And this is all there is to it. And I want to bring up the node tree. So this is our little server visualization. And there you can see our 12 little synths hanging out on the server. So we're going to release them. And there they go. Right? Pretty cool. Now, take a minute and think, okay, what if we wanted to, release them? Well, first things first, I don't want to run this 12 times in a row anymore. Why don't we use iteration again, right? To make this a little bit more easy, right? So instead of manually hitting this 12 times, let's just say 12.do. And we do not want to say x equals, we want to say a equals a.add. Put these in parentheses. Whoa, come back here. And we also need to refresh the array A, because if we take a look at A, this is the language server divide in full display. In the language, we were storing these synths in A. Add a new synth to A, so this array was filled with 12 synths. And then we release them, which causes them to fade out and disappear from the server. But the language is totally decoupled. The language or client side does not know the status of the synthesis objects that they're referencing. So this array is actually still size 12, right? And so since we've faded out everything on the server, it's kind of our responsibility to maintain the language side representation of these objects by, actually emptying the array. Just basically saying A, forget it. A is now a new array. Those things don't exist anymore. And then we're going to say 12.do, and let's make this into a whole tone scale, just for a little bit of variety. It kept picking the same note twice in a row. I'm trying to put some more notes in here. So now it's like a whole tone scale, right? So let's do it. Ooh, sounds kind of funny. All right, and now let's say we want to release these, but we don't want them all to release with a 3-second fade out. We want them to release, some quickly, some slowly, kind of random, right? Or we can just say xbrand somewhere between 1 and 10 seconds. And I want to look at the scope too, because this will be fun. Let's do this. Oh, and I think I turned the volume down, didn't I? So let's bring this back up. So there's our signal, our 12 things, and we're going to release them so they all fade out in a different way. All right. 1, 2, 3.choose would work. Those just have to be square brackets instead of parentheses. And you would just be saying either 1, 2, or 3 seconds. This way we have a sort of more interesting, this could be all sorts of numbers. But yeah, the array 1, 2, 3 would definitely work. All right, and there's one last thing I want to do, and just, we've only been doing one argument at a time, right? Just setting freak or this or that. We have this thing called boost. Let's make an argument called pan. And let's say, let's also make an argument called amp. And so pan is going to be 0. You know what? I don't want to disturb what was up there too much, so I'm going to copy it and bring it down, trying to preserve previous work. So we'll take this, and down it comes. And this will be the last thing we do. Then we'll move on to envelopes. So we're going to say pan initially 0, amp initially 0.1, and we'll plug those in here. Right. And all right, so let's take this 12 synth idea. And we were zeroing out this array, and we're going to say add to the array one of these synths. And I'm going to make even more white space here for myself so I can really kind of see what I'm doing. Trying to manage my indentations. Let's put that there. Okay. Now, when we made this example up here, right, and we said set freak to 220. Let's say we want to also change boost at the same time. We could do it separately. Like make that 8 we could change both simultaneously. Like, let's say this is now 400 and this is 8. So we can do multiple sets in a single line. We don't have to do one at a time. We can just say this argument name, this value. Now that argument name, that value. And we can do random stuff too. Say that, and let's say X brand 110. So now it's not just the frequency that's changing, it's also the timbre. And just want to add that basically what we're doing here with this boost and soft clip is we're giving ourselves the ability to smoothly transition between sine wave and square wave, right? Because the more we boost and soft clip, the more that sine wave sort of approximates a square wave shape. So it's just kind of an interesting timbral thing we can do. Let's go back down here. We've got our function with all 4 arguments. And now what I'd like to do is do something totally sort of a nice rich amount of randomness here. So let's do I want to do something musical, but I don't want to do too much work. So let's just make a nice big array of open fifths. And I don't know how high we want to go. Maybe up to like 85. That's probably not a... It's fine. It's going to do the math for us. Okay, so we have 8 pitches to choose from. We're going to make 12. We'll pick a random MIDI note, convert it to cycles per second. Boost will be something between 1 and 8. And pan, this is going to be nice, will be something between minus 0.8 and positive 0.8, because remember, pan is our pan control, with minus 1 is hard left, positive 1 is hard right. So we're going to do a pretty wide spread, but not a full spread. And then amp will say just, let's give a little bit of randomness here. So they might be really quiet. They might be a little bit louder. All right, so let's just back up a second. We've got our function here. We're making a new empty array, and we're iterating 12 times. We're going to perform the following function, this function here, 12 times. And each time we're going to add a new synth to the array by playing our function and providing some randomly selected value for each one of these. So I am kind of excited to see what this is going to sound like. And let's go get this. Yeah, and the last thing I want to do before we move on to envelopes, I know I said it was the last thing I want to do, but there was one additional thing in the play method for function. Now, we're only dealing with args and specifying initial arguments, but there's also something called fade time. So we can sort of drop this down a little bit and also say fade time, and then it's exactly like release, except it's the attack instead of the release. So we can say xbrand 3, 6. All right, so now each one is not only going to have these randomly, algorithmically chosen argument values, but it's also going to have a random fade time. Very easy to get carried away here. Let's say, I just can't help myself. We're going to subtract either 0 or 2 from this. Okay, so we have that minus that. So our frequency is something in here minus, or we might subtract 2, we might not. Choose minus da. What did I do? Yeah. Yeah. Oh. Well. Yeah, I think what I just need to do is I'm choosing the number. And then I'm subtracting one of those things. I've made this far more complicated than it's supposed to be. So we pick one of those, and then we subtract one of those, and then we're just going to convert that. Right? So we pick a random MIDI note. We possibly subtract 2 from it, maybe not, and then we convert to cycles per second. All right, so on the rewatch, come back to this screen, pause it, and copy this if you want. And there's a lot of fun things you can imagine and do with these arguments. But let's move on to envelopes, shall we? We have been taking advantage of the fact that when we play a function, an envelope is created for us, which is what allows us to do things like fade time on the way in, which allows us to release on the way out. But we are going to make our own envelope, and we're going to modify this function to do so. Right? And I want to talk about 2 basic kinds of envelopes: the kind that have a fixed duration and just simply go from beginning to end, and the kind that can be held, sustained at a particular value, like an ADSR envelope. All right, envelopes. We're going to make an envelope, and that's going to be a signal, and we're going to control the amplitude of the signal by multiplying the envelope by the signal. So the first thing I always recommend doing is declare another variable, right? And we're going to make an envelope. Now the unit generator for this is called EnvGen. This is a signal generator, which is basically optimized for creating custom envelope functions, envelope shapes, which can be used to control any number of parameters. So we're going to have something that looks like this. And then we're going to, at the very end, say sig equals sig times env. At some point, we're going to take this envelope and multiply it. And so envelopes require a little bit of an introduction. Basically, an envelope takes a bunch of arguments, but the first one is simply called envelope. So the first thing in here is an instance of a class called env, which is essentially an object which represents a breakpoint envelope function. And we make a new envelope by saying env.new. And env.new is sort of the basic envelope creation method. And it expects 3 arrays, sort of at minimum. This array contains the levels. So for example, we might start at 0, go up to 1, go down to 0.2, stay there for a while, and then go back to 0. So these are basically the points along the envelope, the breakpoint envelope function. The next array corresponds to the times in seconds between breakpoints. So for example, this 0 to 1, it's going to take X amount of seconds to get there. Let's say 1 second. And then it'll take maybe 2.5 seconds to get down from 1 to 0.2. It'll stay there for another 2 seconds. And then over 3 seconds, it'll fade out to 0. And this next one represents the curve between breakpoints, or in other words, how the line is interpolated. Is it a straight line? Is it curved? Is it, whatever? And for now, I'm just going to put zeros because this is going to make it easy to explain later. And we could just run this line by itself, run this clump, but it's not going to do anything. So I'm going to use the method plot to actually visualize what we've made. So we have an envelope. It goes from 0 to 1 over 1 second. It goes down to 0.2 over 2.5 seconds, stays there for 2 seconds, and then fades out over 3 seconds. So it's a basic envelope. It looks kind of like a kind of weird ADSR that's out of proportion. Yeah, attack, decay, sustain, release. Now the zeros I feel like the first two arrays are pretty self-explanatory. The zeros mean linear interpolation. So let's just go ahead and change this second segment. We'll make this a 3 instead of a 0. Now we have this kind of a shape. Yeah. So we've changed the curve. We can make this, let's see, I'm going to make these appear, hello, right on top of each other. So we had 0. I'm going to adjust this. And then we said 3, right? And then we have, let's say, 8. So positive numbers cause the curve to bend in such a way that the curve changes slowly and then very quickly at the end. So negative numbers do the opposite. They bend it in the other direction. So negative numbers will cause each segment to change very quickly at first, just kind of shoots to the next target value and then levels out as it goes. So we could make this one do that kind of thing, and we can make our release do that kind of thing. It really doesn't make any sense to change the curve of a flat line because it's a line, it's a flat line. How do you bend that, without changing its values? You can't. So this segment between 0.2 and 0.2, there's really no point in changing it. Okay, so let's say this is our envelope that we're working with here. Let's close these windows. Now, how does it work? Well, we are going to simply drop this env into EnvGen, like that, right? So env is a unit generator. It's EnvGen running at the audio rate. And so it's going to generate an envelope signal based on this abstract envelope shape with all these specific values here. Right? So let's make that function, and let me just grab one of these lines from earlier. Let's not make 12. We'll sort of just give me that one. That'll do fine. I don't know why I couldn't just type that, but I guess I just lazy, I guess. All right, so now let's here we go. Yeah, so it did the thing. Right, let's do it again. Yeah, so 1 second up, 2.5 seconds down to its sustain level, 2 seconds there, and then a 3-second release. Let's do it. Let's say args, freak, xbrand, 50, 500. Okay, so that's the gist of envelopes, but there is sort of a problem here. As you can see on the server, these things are just piling up. There's no sound, right? There's no levels. There's nothing on the scope, but these synthesis processes are still existing, and they're still actually running. So if we were to, just say do 12.do, just make 12 of these again. Sounds kind of nice. Right. Wow, that's a lot of things, isn't it? We've made so many. And if you look down here in the bottom right, it's our sort of peak server, our peak CPU usage is like jumping around between 7 and 15. And if you rewind this video, if you on the rewatch just drop back 20, 30 seconds, you'll see that it was kind of like at probably 0.5, maybe 1%, just kind of idling. So all of these things we've made, we're not hearing anything and they're done, but they're still taking up precious CPU space. So this is a real problem. Now we can hit command period and there they go, right? They're gone. But it would be really great if we could have this process of going poof off the server happen automatically. Needs garbage collection or something like that, right? So this is where doneActions come into play. And doneActions, a doneAction is a way to tell a UGen that is inherently finite, like an envelope, for example, but it's not the only kind, what to do when finished. So there's a bunch of unit generators, like the ones you see here. We've already maybe seen line and xline a little bit, EnvGen. play buff and buff read. These are UGens that read an audio file from your hard drive or whatever. And these all sort of are unified in that they have a beginning and an end. Now, compare this to like a sine wave or a pink noise generator, which just runs forever. It does not need to know what to do when it's done because it's never done. It just generates, right? But envelopes are finite. This kind of envelope is. So when one of these UGens is finished, it provides the opportunity for the programmer to say, here's what to do when you're finished. And here are the actions you can do. There's actually, I think, 15 altogether, 16 altogether, because they started 0. The default done action is 0, which means do nothing when the UGen is finished. And that's what was happening here. The EnvGen was finishing, and it was like, okay, I'm at my end. My last value is 0, so I'm just going to, do you want me to keep doing zeros? Okay, do nothing, great. So it's just spitting out zeros, and these zeros are getting multiplied by our signal. And so that's why we hear nothing, but they're still cranking away. You know, they're still doing their thing. So this is where done actions come into play. Now, even though there are 16 different done actions, the only done actions I've ever used are 0 for do nothing and 2, which is free the enclosing synth. Think back up here when we were doing x.free. That's the action. So instead of having to manually say, the envelope is done, I better type x.free and take care of that, right? This way, as soon as the envelope finishes, gets all the way down to its last segment, it says, bam, hey, synth that I'm a part of, disappear. And you know, everyone inside of it, you're gone, right? So let's do that. EnvGen takes a bunch of arguments, envelope, gate, level scale, blah, 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 blah. The last one is done action. And so we're just going to say comma and skip right over to done action by saying done action : 2. Now you can do, I think you can do done.free self. I think that's like it reads a little bit nicer, right? It's like, I'm going to free myself when I'm done. But I have always been in the habit of saying done action 2. And if you watch my tutorials, and I think a lot of other people's work, this is just the ability to use these names is relatively recent, and so many people are doing done action 2, and you'll hear me say this, done action 2, done action 2, done action 2, over and over again, because it's so valuable, right? The sound is done, the envelope is finished, the signal level is at 0, done action 2. So now let's take a look at how this works. Poof, there they go, right? So now we can just kind of go crazy. We don't have to like store these in an array and release them later or manage them because they free themselves. It's like a self-cleaning kitchen or something. It's like you're making dinner, you're cooking dinner, you're eating dinner, and the whole kitchen's a mess. But if you say kitchen, your done action is 2, then it will automatically clean everything up and put everything away in the cupboards when you're done. So wouldn't that be great? So that's kind of like what done action 2 does here. All right, let's see if I can very briefly, I think I'm going to save gated envelopes for next week because it's going to be a bit of a discussion. So we'll get into like sort of true ADSR envelopes, the ones which sustain indefinitely, next week. It's a good topic, and we'll start there next week for sure. What I want to do with my remaining 4 minutes here is talk about the difference between AR and KR. And actually, I think, no, we want to go to the UGen help file. Yes. So UGens take one of 3 rates: audio rate, control rate, and initialization rate. And we're going to focus on AR and KR. Yes, they are like C sound. They're exactly like C sound. So AR UGens run at the sample rate, which in my case is 48,000 samples per second. So we get 48,000 samples per second of a sinosk.ar, a white noise.ar, etc. KR UGens are different. They have a lower resolution because they only output values at the control rate. And so audio is processed in digital audio systems in blocks. And the default block size in SuperCollider is 64 samples. So this means control rate unit generators only output a value every 64 samples. So think of them as like a lower resolution image. Now I'm going to actually plot something here, which I think will be useful. here is a plot of two sine waves. The top one is AR, the bottom one is KR. They're running at 10 hertz, and we're looking at 1/10 of a second, so we only see one cycle. Now, they should look and effectively are exactly the same. Now, they're not exactly the same, but the differences here are so minuscule that they're completely ignorable. So let's ramp up the frequency. Let's do 2 cycles in the course of one plot, right? So now they're both faster frequencies. Again, they look the same, right? Let's go to 50. And let's really make good use of my second monitor here. So now you should be able to see a very, very subtle difference between the top and the bottom. The top one is smooth, or as smooth as can be, sort of in a digital context. This one is starting to look a little bit polygonal, right? It's got these corners, especially at the top and the bottom, starting to look a little jagged. Let's go 100. And now we can really, come here you, we can really start to see the difference. So this is both of these are 100 hertz sine waves, and we're looking at 1/10 of a second. And since I'm running at a sampling rate of 48,000, that means this plot contains 4,800 samples. Now I do not have 4,800 pixels across my screen, so there's sort of more samples than can be represented by pixels, so it looks very, very smooth as possibly can be on my display. Now a control block is 64 samples, and 4,800 divided by 64 is 75, I think. And so if we divide 64 by 48,000, this gives us the amount of time in one control block, which is just over 1 millisecond. And these blue bars are spaced at 5 milliseconds. So actually you can see right here, that's one control block. And then right here, that's a control block. And right here, that's a control block. So these are the only values we get from this control rate SINOSC. And the best we can do is just say, I don't know, let's draw some lines, let's connect the dots, right? But it does not capture the true resolution of a sine wave. It's low resolution. Let's go all the way up to 200. And yeah, so now it's starting to look really cruddy. It's just kind of garbagey, right? It's no good. Let's do, just for fun, let's do like 900 or something. All right, so we got to spread this out. A lot of pixels to plot, so it's kind of laggy. So this is a phenomenon called aliasing, or fold over, where the control rate is so slow compared to the frequency of the tone being generated that it just doesn't have anywhere near enough resolution to represent this wave. So here's the sort of the practical takeaway with audio rate and control rate. If you want to listen to a signal, basically send it to your speakers, it must be AR, because these level meters here, they correspond to audio output buses. You can only send audio rate signals here. You can't send control rate signals there. If you have a signal with a fast frequency, I use that term kind of loosely, like if it's sort of 100 hertz or more, you know, you could do the math, but just if you consider it to be a fast moving waveform, it's like got zippy little corners, fast oscillator, use AR to capture that resolution. Now, if you have a signal that is a slow-moving signal, like an LFO controlling a filter, like a wow, 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 something like that, you know, one hertz, or if you have a signal that is a long envelope, long fade in, long fade out, those can be control rate, because as you saw with the sine waves at 10 hertz, you know, it's just it's slow enough compared to the control rate, you know, which is fast enough to represent 10 hertz. There's no problem. They look exactly the same, you know, no problemo whatsoever. But if you have a fast waveform with like quick changes, it's good to use AR. So that's basically the difference. Okay, so that's the end of class. So anyone who's sort of, you know, taking this class just for the lecture and what's going to be covered on homework and stuff like that, feel free to check out. But I know there was a lot of chatter in the chat today, so I want to kind of go back and address questions people might have had. I'm going to try to roughly work my way backwards. You can change the block size, Daisy Stomper. The block size is just 64 samples by default. So, for example, you can theoretically lower the block size to 1, which means there's one control block every sample. In that case, the audio rate and control rate are the same. So the benefit there is that control rate unit generators have a greatly improved resolution. The downside is that you're asking a lot more of your processor. There's these basically audio callbacks happen, constantly. So it's a balancing act. You want your control rate to be like kind of fast enough to be able to represent slow moving signals, but not so fast that you're just exhausting your processor. And yeah, Brandon, envelope, to apply an amplitude envelope, you just multiply it by the signal. It's really quite simple. It's simple and elegant. There's really nothing more to it than that. So yeah, I guess that's it there. If no one's got any follow-up questions, I hope this gives you a few more tools for making some interesting creative sounds. Feel free to mess around with the code you saw here, add some more arguments, add some more synthesis nuance, take the sine wave, add it to pulse wave, and I don't know, do all sorts of fun stuff. So I'm about 70-80% done with the homework for this week. I'll post it on the video description, and I'll also post the answers for week 3. And yeah, I think that's going to be it. So thank you all for watching. I actually made a little one of these things. So yeah, thanks for watching. Hope you enjoyed this. I'll be here same time next week for week 5. And that's going to be it. See you next time.